In the vast universe, there are mysteries that challenge the way we understand space and time. Black holes, these giants of the universe, born from the death of massive stars, are powerful enough to disrupt the fabric of reality. Imagine a powerful force that absorbs not only matter but also light, making the weather conditions invisible. The quest to discover the secrets of black holes has pushed people to the frontiers of astrophysics and advanced the frontiers of technology and theoretical physics. As we enter a new era of discovery, the mysteries of black holes continue to amaze and challenge our understanding of the universe. The advent of space technology, especially the James Webb Space Telescope, JWST, is a new phase in the exploration of these giants. Launching in 2021, JWST will mark a major leap in our ability to peer into the darkest parts of the universe, capturing light that has taken billions of years to reach us. This state-of-the-art instrument, with its powerful infrared capabilities, will provide unprecedented insights into the formation and evolution of black holes, revolutionizing our understanding of these mysterious entities. With each new discovery, JWST reveals layers of the universe's history hidden by dust and darkness, challenging current theories and revealing the complex interactions between black holes and their environment. Black holes, by their very nature, defy direct observation. Their gravitational pull is so strong that light cannot escape their grasp and cannot be seen against the background of space. The largest of them, known as supermassive black holes, are located at the center of galaxies with masses ranging from 1 million to 1 billion times that of the Sun. The origin and evolution of these giant creatures is still the subject of great research and debate among astronomers. They are believed to be formed from the remnants of dying stars, but the exact process of their formation is shrouded in mystery. The complex dance between matter and energy of these cosmic giants is still not fully understood, so research and speculation continue. A major moment in the study of black holes occurred when the first image of a black hole was captured in 2019 by the Event Horizon Telescope, EHT, a radio network of the world. Telescopes were able to create a virtual view the size of the Earth. The image, which shows a bright ring of light around a dark shadow, confirmed the existence of a supermassive black hole at the center of the galaxy M87, about 55 million light-years from Earth. This early appearance not only provided evidence of black holes, but also confirmed many of the predictions made by Einstein's general theory of relativity. A successful record of this kind is a major milestone in astronomy, a new way to study black holes and their role in the evolution of galaxies. The discovery of Cygnus X, one in 1964, was another turning point in the study of black holes. As the first strong candidate for a black hole, Cygnus X1, located 7,200 light-years from Earth in the constellation Machias, is a supermassive black hole. This discovery, although smaller than the supermassive black holes, showed that black holes are not just artificial but real and observable. Cygnus X1's existence was determined from X-rays emitted by material from its companion star, which is very blue. The discovery was met with excitement and skepticism, as demonstrated by the famous bet between the famous physicists Stephen Hawking and Kip Thorne in 1975. Hawking, due to his cautious nature, says that Cygnus X1 is not a black hole, as Thorne knows to know. Over time, as more evidence was collected, the existence of Cygnus X1 was confirmed as a black hole, which became an important topic for the study of black holes and their properties. The challenges of studying black holes go beyond discovering how they exist. Unlike stars, black holes do not emit light and are invisible against the background of the universe. Detecting black holes requires looking at their effects on nearby objects, such as the motion of stars and rotating gas clouds, and detecting the X-rays emitted by materials in the time being pulled into the black hole's accretion disk. This is a very difficult task, because X-rays and other types of radiation are so weak that they are drowned out by cosmic noise. The great distance of many black holes makes detection difficult and requires sophisticated equipment and techniques to detect faint signals of noise. The advent of space observatories such as the Chandra X-ray Observatory and JWST has greatly improved our ability to find and study black holes. These observatories can observe the planet in wavelengths of light that are blocked by our atmosphere, such as X-rays and infrared, regardless of the distortions caused by the Earth's atmosphere. This ability has allowed astronomers to study black holes in greater detail, leading to new discoveries and observations. One such discovery is Gaia BH3, a dormant black hole located 1926 light-years from Earth in the Milky Way. Gaia BH3, identified by analyzing data from the European Space Agency's Gaia mission, was not discovered until JWST and other observers provided data to confirm its existence. This black hole, which is not capable of absorbing material and therefore does not emit much radiation, demonstrates the capabilities of modern telescopes and the ability to detect other giants hidden within in our world. JWST's ability to study the early universe and the formation of the first black holes is one of the most exciting things. The first universe, a few 100 million years after the Big Bang, was a time of intense activity and the formation of the first stars and galaxies from primordial clouds of gas and dust. Recent observations by the JWST have provided tantalizing glimpses into this distant epoch, including the detection of an extremely red supermassive black hole located about 12.9 billion light-years from Earth. Estimated to have a mass around 40 million times that of the Sun, this black hole challenges existing models of black hole formation and growth. The existence of such a massive black hole less than a billion years after the Big Bang suggests that black holes can grow much more rapidly than previously thought, raising questions about the processes driving their rapid growth and their interactions with their host galaxies. This discovery also brings to the forefront the fundamental question of whether black holes or galaxies formed first, a dilemma often referred to as the chicken or egg problem in cosmic evolution. The exploration of black holes not only enhances our understanding of cosmic phenomena, but also drives the development of new technologies and methods. As astronomers push the boundaries of what we can observe, they are constantly developing more sensitive instruments and innovative techniques to explore the extreme conditions near black holes and gather more detailed data about their properties. One exciting area of research involves the study of gravitational waves, ripples in spacetime caused by massive objects like black holes merging. Detectors such as LIGO and Virgo have already observed several black hole mergers, providing crucial information about their sizes, frequencies, and the nature of these cosmic events. The ability to detect and analyze gravitational waves offers a new way to study black holes and test theories of gravity, opening up new avenues for understanding the universe. As observational technology continues to improve, future missions and telescopes are expected to provide even deeper insights into the behavior of black holes and their interactions with their surroundings. These advances will likely reveal new aspects of black hole physics, including their role in galaxy formation, the nature of their interiors, and their ultimate fate. The study of black holes remains a dynamic and rapidly evolving field, capturing the imagination of both scientists and the public alike. Each new discovery pushes the limits of our knowledge and reveals more about these mysterious cosmic giants, ensuring that black hole research remains one of the most exciting and transformative fields in modern science. Moreover, the ongoing exploration of black holes touches upon the theoretical implications of fundamental physics, particularly the reconciliation of general relativity with quantum mechanics. One significant area of interest is the information paradox, which questions whether information about matter that falls into a black hole is lost forever or if it can be recovered. This discussion examines the structure of reality and examines how information is preserved and destroyed under adverse conditions. In addition, the study of black holes provides valuable insight into dark matter and dark energy. By observing the effect of black holes on their environment, scientists can determine the presence of these complex particles in the universe, and may solve some of the world's most profound questions about the creation and the tragedy of the world. As our observations expand, black hole research may discover new types of black holes or new phenomena. For example, intermediate mass black holes, which are intermediate to massive mass, remain elusive but may provide new insights into black hole formation and evolution. Also, the possible discovery of ancient black holes that formed the early universe could shed light on the conditions of the early universe and the formation of the first galaxies. In fact, the continued exploration of black holes will not only expand our understanding of these giants of the universe, but also push the boundaries of our understanding of the universe at large. Each discovery raises more questions and strengthens the search for answers, ensuring that the study of black holes is one of the most exciting and revolutionary areas of modern science.